So we are moving on. We finished up the chapter that pertains to graphing the various trigonometric functions on a standard XY plane. We went through sine and cosine, various ideas and components of sine and cosine, such as various shifting components, period, pieces, the way in which we can ultimately construct a one-period interval. Moved on to tangent and cotangent, a few different characteristics, a few similarities. And constructed those, and remember for secant and cosecant, there was no homework for that section, and the only stipulation is that you know basic characteristics about the graphs. It would be a very simple question if I asked anything about secant and cosecant, which I'll talk about more so whenever we get around to that pesky Unit 3 test review session, which is, it won't be a week from today. That's pretty much all I can say for now. It depends on how much stuff I get done. But via the syllabus, I am required to inform everyone a week ahead of time of whenever the Unit 3 test will be. And additionally, if you have the homework for the graph of the tangent and cotangent stuff, if you haven't turned that in by now, please go ahead and do so as soon as you can. So other than that, that's really all I have as far as announcements before we start this lecture. Does anyone have any questions for me? If not, we're moving on to a new idea, a new way of tackling problems. As before, we pretty much were tasked with making very careful identification of various components of trig functions. Now this idea is pretty much independent. And as you notice on here, there's just a bunch of formulas right in front of us, right here. So what's the point of all of these formulas? Why are they there? Why are we looking at them? And so one of the interesting aspects of trigonometry is if you have a various number of trigonometric functions you're dealing with in some expression, sometimes you want to simplify them and end up realizing that there's simplification ends up giving you something a lot nicer to deal with, something that's a lot more efficient to deal with. And so these formulas really help us in an algebraic sense. So this whole chapter is going to be very algebra heavy. You don't like algebra? Well, I don't know what to tell you. It's not going to be anything crazy algebraic, but this will be an algebra heavy chapter in general, especially this first section. I think the next one's not as much, but we will be taking larger expressions and simplifying them down to their most simplistic terms. And what we will use to help us in that pursuit of simplification comes down to, well, we'll be using some of these formulas here. And so if you like a nice compact place for all of the formulas to be at, here's one. I'm not going to give you a formula sheet for the Unit 3 test because, I mean, frankly, I'm not supervising it. So, the Unit 3 test, whatever it is, on the syllabus it says the Unit 3 test is unproctored. It means I am not proctoring, I'm not looking at what you're doing. So virtually that means it's open, whatever. I don't care. So here is perhaps a compact place for some of your formulas. If you held onto the formula sheet from the midterm, that might be helpful as well. If not, I might have a few copies with me if you want that. But I think that's a good introduction. So let's go ahead and let's look at a new set of formulas. And it's something called even-odd identities. So, just curious question. Who's coming in here straight out of college algebra? Anyone?
Well, I took college algebra my junior year, and then I didn't take math.
Well, for those of you who may remember college algebra, you might remember determine if the graph is even, odd, or neither. Maybe you remember that. Maybe you don't. And that's okay if you do or don't. Because what that represents is ultimately types of symmetry. But more so, there's an algebraic way of determining whether a function was even or odd. Now, we're not really going to go into those characteristics too much. We're going to skip straight into the formulas. And so a nice way to derive this, so there's already an illustration drawn here. I'm just going to redraw it on another canvas. So I think it's a nice derivation. It will motivate the proof style of solving for something, proving that something may be equal to another thing. And so what the motivation is you have your standard XY plane, and let's just say you have some angle. So let's say this is your angle. Call it theta. So what do you normally do in a situation like this? Well, generally you triangulate. You figure out whatever the x value is, figure out whatever the y value is, and the r value. In fact, for reasons you'll see momentarily, I'm going to move the x inside. Now, that's how we normally figure out something for sine. If we were trying to figure out sine of theta, we would draw out this angle, we would triangulate, and all of this fun stuff. So sine, hopefully you may recall. Oh wait, why do I have r here? Let me not lose my job. Something so ridiculous. Okay, there we go. Sorry. Okay, let's try that again. So y and r should be switched, so please switch it. Okay, so sine is opposite over hypotenuse. So very basic stuff. So now the question is, what about if we looked at not theta, which is the regular angle, but what about if we looked at or tried to consider what negative theta would be? If we made the angle completely negative, what would happen? That's the question here. And so for an angle to be completely negative, negative angles go in a clockwise direction. So in a clockwise direction, the angle would go out to here. That's what happens whenever you look at a negative angle. You go in a negative or a clockwise direction. And so what would we do if that was its own angle? We could triangulate where the x would be the same, but the y would be negative, and the r would be the same. Because instead of the y going up, the y value is going down, but the x is still going in the same direction, and the r never changes sign. R is always positive. So if this was the angle we were looking at, then sine of negative theta, well, what's opposite? It's negative y. What's the hypotenuse? It's r. So between what we've drawn or constructed here, the correlation between these two sine of theta functions, they only differ by a negative sign. And so What we cannot say, in fact, so what is not true is obviously this. So what I wrote is a true statement because I put not equals. And obviously that's the case because these two quantities are not the same. How can we fix that? We do this. I added one little minus sign. And now, what that shows us is a formula that we just derived on our own. And so we can honestly do the same thing for cosine as well. Cosine of theta, remember theta being the top angle, it's adjacent over hypotenuse. And what about cosine of negative theta? Just this one over here. Adjacent here is x, and that's still over the hypotenuse, r. That's kind of interesting. They look the exact same. So what that means is that this whole time, if you ever had a negative in your cosine, you can just take it out and nothing changes. Wait, thinking, really? I could have done that the whole time instead of this coterminal crap? Yeah, you could have done that the whole time. But that's only specific for cosine. Notice sine does not have this, but cosine does. So the reason why I derived it like this so carefully is to motivate really the proof aspect of where we're heading towards. We're not necessarily just sticking numbers in or just getting some number as an output. We're trying to now prove things. We're trying to show that two things that look completely different are in fact the same by showing the bridge that connects the two sides together. That's the nature of, well, if you want to generalize it, that's the nature of logical thinking, the philosophical branch of logic that deals with the careful sequential organization and connection between what seems to be two independent thoughts or ideas. So logic is the philosophical branch for which all mathematical analytics tends to fall under, for good reason. But if everything I just said sounds completely boring, all you need to get out of what I said is that these two formulas are now formulas we now have in our mathematical lexicon of formulae. And you might think, hey, I should probably write those down. Those are kind of important. Well, no need. And then the cosine one is right underneath. So everything I just said is here. So there's nothing really to take from that more than food for thought. And going to example one, which might require a little bit more brain power, use the even-odd identities that we just found and figure what the other formulas would be for, say, tangent or cotangent, cosecant and secant. I'm going to start with trig tangent. So basically it wants us to figure out if we replace the theta in tangent with a negative theta, like we did for sine and cosine, what can we do with that negative sign? Can we bring it out to the very front, like we did with sine, or does it disappear like cosine? Or does something crazy happen? We'll find out. So the problem says we need to use sine and cosine in order to take this problem further. Now I have a tangent. I don't see a sine or cosine anywheres. Well, it's a good thing that tangent can be broken down into sine and cosine. How can it be broken down? Use a quotient identity. That's when all of these formulas are, you're going to need to have these formulas close at hand as you go through these, because some of them might appear rather arbitrarily. But noticing that tangent can be broken down, and we're going to be using this one a lot. This one's going to be used quite a bit. So you might as well get used to that quotient identity, as it's called. That tangent is sine of theta divided by cosine of theta. So what does this tan become? It's sine of negative theta, because whatever goes here has to go here, divided by cosine of negative theta. And so we know what happens to the numerator and the denominator, because the numerator part, well, we've already derived that one. It becomes negative sine of theta by that even odd formula. And then that is divided by cosine of theta. Notice for the cosine one, the negative sign disappears because we just derived that one. So this is the beauty of the constructive nature of mathematics, for which we can derive new information from stuff that we have already determined. It's more so called an axiomatic approach, as we make some base assumptions and make a constructive, I guess, system using those assumptions, as well as the subsequent or consequential results that follow. And then now that we have negative sine of theta over cosine of theta, the kicker is we can bring the negative out, and sine over cosine is just tangent. So I'm going to do one more. Cotangent is very similar. So I'm going to do, let's do cosecant. So if we swap out theta with negative theta for cosecant, then what happens to cosecant? Well, now we know sine, cosine, and tangent. How do we get cosecant to be sine, cosine, or tangent?
Do you use reciprocal identities?
Yeah, so cosecant, this is from the very beginning. Cosecant is 1 over sine of whatever the angle is. But hey, we know what happens to sine. It means we bring the negative sign out. And then the negative comes out, while 1 over sine goes right back to cosecant. But now with the theta by itself. As you all probably have noticed by now, the formulas are just right below. So now on top of those formulas I had above, there's some more formulas. So there's some more formulas. So this is all, and the way we have derived these is all part of the proof aspect. We took one side, we simplified it using formulas and things that we knew, and we hit another side. We got to another side. And this is the theme of this section. So it uses quite a bit of algebra. So another issue that may arise as you're doing homework questions from this section, homework questions from this section, is that what does it mean for something to be simplified? What end goal are you trying to reach? Because simplification in algebra is sometimes more quantifiable than, say, in trigonometry. What does it mean to be simplified? It's not always the most straightforward question, because even example 2, I could rewrite that in several ways. I mean, ultimately, example 2 simplifies to something very concrete, as you'll all see momentarily. But for example 3 and so on, it might be kind of vague. And so really, the closest way that I can try to define simplification is this little footnote that I put here. You write an expression in terms of sine and cosine, and you simplify that, and then the way you conclude your problem, there better not be a single fraction. No fractions. This is generally the process. I mean, there might be some nuance, but that is the closest to sort of streamlining this as I can get in the most condensed amount of wording. So let's apply that directly to example 2 here. So we have this expression, and it just says simplify. What does that even mean? Okay, well, let's look at the footnote. Write an expression in terms of sine and cosine. All right, so let's do that. Secant. How can we write secant in terms of sine and or cosine? Secant is just 1 over cosine. And then cotangent. How do we write that in terms of sine and or cosine? Well, cotangent is cosine of theta divided by sine of theta. And you can find that on the first page of this section. So, all the way up here. Notice these formulas come up, and as they come up, you need to be more and more familiar with them. And then finally for sine, oh, that's easy. Sine's already in terms of sine, so not really much to do there. So this is converting everything to sines and cosines. Now we can simplify. Does anyone happen to see any way in which we can simplify what is here?
You cancel out the cosines and the sines and it becomes 1.
Yeah, so this problem's kind of a toss-up. Just, hey, please notice that the cosines cancel and the sines cancel. This is kind of the algebra that comes into play. What are we left with? 1. And that's it. 1 can obviously not be simplified anymore. So example 2 is just the most simplistic introduction. So kind of the versatility of this is if you're trying to build a robot and it has a certain rotation to one of its mechanical arms, and you determine that you want it to move in some way that's equivalent to this expression, and then you end up figuring out, why is the arm not moving at all? Well, it's because if you simplify this, you end up realizing that you get a constant output. So then that's why the arm is remaining static the whole time And then you have to go back to the drawing board and figure out, well, shoot, where did I go wrong in my computations? I don't know, I think that's kind of cool. So from here, let's look at example 3. So example 3, it's another one. It's tangent plus cotangent. You might think, all right, that already looks kind of simplified, which it really does. It looks pretty simplified, but simplified relative to the way the book is mandating for us to simplify it. The first thing, we convert to sines and cosines. So we'll start with tangent. How do we convert tangent to sines and cosines?
Sine over cosine.
Sine of, don't forget the of theta part. You put sine over cosine like this. I'm gonna, probably gonna bitch at that. So don't put just sine over cosine. It's sine and cosine of theta. It's just like putting f of x. You just put f. I don't know. That's a nitpick. So that's the tangent part. And then there's a plus sign, and then cotangent. Simply, well, cosine of theta divided by sine of theta. So that's the first step, converting everything to sines and cosines. Now the question is, how do we simplify this?
Wouldn't it be 0?
What's that?
Wouldn't it be 0 because they would all cross out?
So that's only if they're multiplying. And if they did, it would be 1. So if they were multiplying, the cosines and the sines would cancel. But they're adding. So let me ask it a different way. If I were to add 3 over 4 plus 4 over 3. I claim this is almost the same problem. How would I do this? And don't say put it in my calculator. So how would I do this if there were no calculators? We had to do this the old grade school way.
Common denominator.
A common denominator. So you'd have to use a common denominator.
12 would be
What's that?
12 would be the least common.
Yeah, so, we'd have to use a common denominator to bring these together. So let's see, it'd be 12. Yeah, 4 and 3, they both go into 12, and then 4 times 3, so that's 9, plus 4. So what is that? That's 4 times 3 is 12, and then 4 times 4 is 16. And then you would have 9 plus 16 over 12. So now back to trig. How does that apply here? Well, obviously, common denominator. What is the common denominator? How did we get the 12? Twelve is 4 times 3. That's the product of the two denominators. So how do we get the common denominator? It's cosine times sine, or cosine of theta times sine of theta. So least common denominator is cosine of theta times sine of theta. This is when that algebra stuff starts coming back into play. So I'm just going to rewrite the first one. What do we have to do to that first fraction to get the denominator to be cosine times sine? What did we do to the 3 over 4 to get it to 9 over 12?
We multiply the bottom by the top. or the bottom by your. Yeah.
We multiply, the denominator's missing sign, so it needs a sign. But whatever you do to the bottom, you have to do to the top. Because that's the same thing as multiplying by 1. Multiplying by 1 doesn't change anything. So what about the cosine of theta over sine of theta that we had? Because its denominator is missing something, missing a cosine. So what about if we just gave the denominator a cosine? But then we have to give the numerator a cosine, because we have to balance out the problem. So we are intentionally unsimplifying the problem at first, which seems really weird. We are intentionally making reducible fractions. But the reason why is for our goal of simplifying the problem at the end. So let's bring all of this together. Remember how fractions multiply. They multiply straight across, numerators and denominators. Sine times sine is sine squared, divided by cosine of theta, sine of theta. That's the first product of fractions. And then there's the plus sign. Now we have cosine of theta times cosine of theta. It's cosine squared of theta. The cosine of theta, sine of theta. And now we intentionally unsimplified the problem because we could cancel, but then we'd end up right back where we started. But now that we have a common denominator, we can add the numerators together, which gives us sine squared of theta plus cosine squared of theta divided by the common denominator. So you might think, how is that more simplified? The answer is we're not done. Because I see a formula in plain sight. You might think, I don't see anything. How about keep this numerator? Just keep an eye on that. Let's go on a trip like that to the formulas up here. Does anything stand out? Wait a minute. It's right here. That whole numerator, it says, hey, well, that whole numerator is equal to 1. Oh, shoot. Let's, that whole part that I have boxed in red here, it all now becomes 1. And then we have one more step. I'm out of room, so I'm just going to put it on the next page. So what we did, we converted everything to sines and cosines. We have simplified, we're simplifying using algebra. And now the last part of the problem says your final answer better not have quotients in it. I see a quotient. That's not good. We need to get rid of quotients. The way we can get rid of quotients, well, cosines in the denominator, what trig function does that correspond to? 1 over cosine. That is secant. The secant. 1 over cosine is secant. And sine is also in the denominator. So what's 1 over sine? That's cosecant. And that is the answer. Again, is it more simplified than what we started off with? By the book's definition, yes. By arbitrary standpoints, simplified form may not be, you know, I don't know. Simplification is a kind of relative terminology.
Is secant or tan theta plus cotangent theta, is that true? Is always going to equal secant theta times cosecant theta?
Yeah, that's a formula. I mean, it's not a formula we have to memorize, but if it were, then what we did was we've proven forever until the end of time that if we follow this system of axiomatic mathematics, then these two things will always be true forever and ever. You can tell I've studied a lot of theoretical math in my lifetime. I don't know anything about cars, but I can tell you about trig functions. Okay, so really it's hard to really patternize these any more than just trying to show you as many examples as I can. And see what you all can do following that. So let's look at example 4 and see how that goes. Now we have sine of theta times cosecant of theta minus sine of theta. So hopefully you might see at least an algebraic step that's going to be coming up. Whenever you have something on the outside of a parenthesis of 2 or more terms, hopefully you remember that verb thing that we do. But before that, let's convert everything to sines and cosines. Well, sine's good. Sine's already sine. And then I see an open parenthesis, cosecant of theta. How do we convert that to sines and cosines?
1 over sine.
It's 1 over sine. So that identity needs to be a little bit, needs to have that one ready. And then minus sine, so that's fine. So again, those signs do not cancel out. This is not multiplication, so we do not get to cancel out those signs. So we're kind of stuck in terms of combining things in that regard. So we need some algebra to help us here. We need to distribute. That's the phrase here. So hopefully you remember from college algebra. This is a case of, if you had 3 times x plus 2, you would distribute and have 3x plus 6. It would be a bunch of multiplication. So it's the same idea here. So distribution means each term we're distributing, or we're bringing in the outer function to each inner one, where they can all be multiplied. And I'll write this out before I simplify. I'll bring this over here. So then it'll be sine of theta. You might already see what I'm going to be doing next, but I'll write it out. I'll put an intermediate step in. That's minus sine of theta times sine of theta. So this is what happens after the distribution. I haven't simplified a single thing yet. I just wanted to show what the distribution will yield. And now we can go ahead and start bringing stuff together and cleaning this up a little bit. So let's start with the first term, everything over here. Well, now they do cancel because this is a multiplication. The signs cancel. We're left with 1. Then there's a minus sign, so I'll put the minus sign. And then I see a sine of theta times sine of theta. Well, you all recognize that. Sine squared of theta. There's two of them. They're multiplying, so it's sine squared. Now, I think something like this comes up. There might be a homework question similar to this. And if I remember from teaching this over the summer, you get to a part that's just like this. And I had a few people that put this as their final answer. I didn't mark anything off for it because I didn't think about it. But we can simplify this even more. And the way we simplify this more, so let's try to remember that. 1 minus sine squared of theta. I'll write it up here. Now I look at the formula sheet and I don't see anything immediately with 1 minus sine squared of theta. However, that thing we used before that says that sine squared of theta plus cosine squared of theta is equal to 1. Well, what happens if I subtract sine squared of theta on both sides? Well, that's kind of interesting. This is what we had. Here it is over here. And it says that we can simplify two terms to become one term, which is definitely more simple, in my opinion. So this is a slight modification to a formula. So we can go down and rewrite this as its final simplified form, cosine squared of theta. So if I ask you that the simplified form needs to be one term and not two terms, then you would be forced to put this as cosine squared of theta. Because 1 minus sine squared of theta is obviously two terms. There's the 1 and the sine squared. Suppose, so again, so I think in this case, the idea of simplification makes a lot more sense because what we started off with is definitely a lot clunkier than what we ended up with. So now let's look at example 5. That one doesn't look very fun, so let's look at it. If anything, I look at that and I think, let me convert everything to sines and cosines. Start off with secant. We convert secant to sine and cosine. Just 1 over cosine. Plus, now I see cosecant. 1 over sine. And then cosine minus sine, they're already in lowest terms. So this is the first step after just converting everything to sines and cosines. Now, algebra. What do we do, Dennis?
Distribute.
It's a certain type of distribution. It's got a special name.
Oil?
Yeah. This is going to be a FOIL. Hopefully you remember from algebra, the FOIL process. It's not very fun, but we have to do it. So remember, it's an acronym that stands for first, outer, inner, Inner and last. Inner and last. So I'm going to do all of that in order, and I'm not going to simplify anything. The first is 1 divided by cosine of theta times cosine of theta. We'll take care of that in a bit. That's the first. And then, really, I'll do this even more step by step. Plus the outer two terms, which is 1 over cosine of theta times, really, negative sine of theta. Because that's the outer term on the other side. It's times negative sine of theta. Plus the inner terms, 1 over sine of theta times cosine of theta. And then finally, plus 1 over sine of theta times negative sine of theta. Okay, so it's a lot. It doesn't look very nice. So let's clean this up big time. We'll do this one term at a time. First term, the cosines cancel. Cancel, cancel, we're left with 1. Okay, so far so good. Next term. 1 over cosine of theta times negative sine of theta. Really, the best we have is negative sine of theta divided by cosine of theta. It's really the best we have so far. Next one, really all we have is plus cosine of theta over sine of theta. And then finally, for the last one, this is a multiplication, so the signs cancel. There's still a minus sign there, so it's minus 1. And right quick, I see that there's a 1 minus 1. 1 minus 1. Like terms, they're gone. Just 1 minus 1. Now we applied an algebraic step. Technically, we could. So this is when things get a little bit ambiguous, admittedly. What does it mean to simplify? Should we get a common denominator and go from there? I say no, because we already did a lot of algebra. And really that's what I'm looking for, is convert everything to sines and cosines, then big algebra step, and then get rid of quotients. So we're just going to get rid of quotients now, because I see 2 fractions. So what's sine over cosine? Tangent. Plus, what's cosine divided by sine? That's cotangent. So, I mean, you could have found the common denominator and simplified it further. And I'm not going to, I'm not going to count off if you want to proceed with this problem further. When I grade these papers, when I grade all of this, what I'm looking for, sine and cosines, some algebra step, and then remove quotients if there are. Here, the algebra step is the FOIL. Combining denominators and stuff, that's an extra algebra step. That's why I don't care about it here. But I did care about it above for example 3, because I needed some algebra step. That's what I'm looking for. conversion to sines and cosines, something algebra, and then remove the quotients. So that's why I cared more about a common denominator in example 3, is because there wasn't a bunch of stuff before it, a bunch of algebra before it. And I try to be fairly lenient on this. Don't think I'm looking for some exact, there really isn't an exact answer for these problems necessarily. Let's look at example 6. Now, example 6 could be really difficult or really easy based off of how you do it. Because you could start to convert to sines and cosines.
There's a formula up there for this.
There is a formula that you definitely want to utilize. So the whole time I've been saying convert to sines and cosines first. But with the exception of if they throw any nice situations at you where you get to apply a formula in the very beginning, that may be very nice to utilize. So let's kind of remember these expressions. 1 plus tangent squared of theta. 1 plus tangent squared of theta. I feel like I've seen that before. Oh, okay, that's interesting. It's right here. You notice now 2 terms becomes 1 term. That automatically makes our life a little bit easier. And then the denominator has exactly this next formula here. So it's saying that the numerator is secant squared of theta, and that the denominator is cosecant squared of theta. And if you can notice that transition, it's going to help you big time. Because trust me, complex fractions with numerous terms in them, it's not going to be very fun. So instead of converting to sines and cosines first, I'm going to utilize those formulas I saw, where the numerator is secant squared of theta, and the denominator was cosecant squared of theta. And then now I'm going to think about sines and cosines. Because trust me, this is much easier to solve for than 1 plus tangent squared and 1 plus cotangent squared. So now, let's go ahead and convert to sines and cosines. How does secant squared of theta become sine and or cosine of something, anything?
Isn't it 1 over cosine?
It's going to be 1 over
Cosine squared.
cosine squared of theta. That is just the numerator. Again, it's not fun, but it would be worse if we did this for tangent and cotangent, I promise. So that's just the numerator. And now cosecant squared is in the denominator.
Sine squared.
That's 1 over sine squared of theta. So this is definitively a complex fraction. But the good thing about this is if you remember that this is simply just flip multiply. This is algebra. This means the same exact thing. You multiply by the reciprocal of the denominator. So you get sine squared of theta divided by cosine squared of theta. That looks, I don't know. I feel like that could be something.
Is it tan squared theta?
That is tangent squared of theta. sine divided by cosine is tangent. And then with the square, well, you put a square. So that definitely is simplified. It's kind of weird that 1 plus tan squared divided by 1 plus cotangent squared just results in tan squared. I find that kind of interesting. So that's something we have now proved for now into the end of time for this system of mathematics. So it's a lot more efficient for a computer to compute tangent squared than it is for it to compute this quotient of values. You have to deal with floating points and blah, blah, blah. Okay, cool. Look at example 7. Okay, so they put a negative sign next to the theta for the numerator only. So if anything, that reminds me of a formula that we can apply. Yeah, so now we remember, okay, if there's a negative within tangent, we just learned a bunch of new formulas. There's a negative inside the tangent. What happens to that tangent? There's a negative inside. Oh, we can bring the negative out. That's what it says. So we are applying a convenient formula before we start with the conversions. So we can take the negative out. And I don't see any other formulas anywhere, so we can start with the sine and cosine thing. So we convert tangent to sines and cosines, which is really just sine over cosine. And that is just the numerator. The denominator is secant. And how does secant convert to sines and or cosines? It's 1 divided by cosine. So we rewrite to simplify this, we can rewrite the numerator and turn this into a multiplication of the denominator flipped. So I don't have my glasses on. Is that your calculator you've been pressing away at, or your phone? Okay. Trying to see how that's helpful. All right, so here we see that the, well, how can we simplify this?
Cosines cancel.
Yeah, cosines cancel. So this simplifies just the negative sine of theta. So that's definitely a lot more simplified than what we had before. Okay. Does anyone have any questions? Well, as far as how to handle this homework, I have 15 minutes left. Okay, so that's not going to happen. So, I was trying to think about having one of these class sessions just be a homework review session. So maybe what I'll do, I'm trying to think what I can do here. I'm thinking about combining these two homeworks together, this one in the next section, but having a homework review session where we just work on problems together from the homework. Because these get a little bit technical, as you all have seen. So I was thinking about, if I get started on the next section, I can probably finish the first page. I can finish the second page next time in class. And then the remainder of class, we can talk about homework questions. And then the next homework will be due the following Tuesday. That's what I'm thinking. I'm gonna roll with it anyways.
So basically, we wouldn't have homework due until not this Tuesday coming up, the one after.
It's gonna be due.
That's very generous. No, I can't make it that far back.
Use.
So normally what I do is I assign homework. Like normally I would assign homework today and they could do the next class period. But I'm gonna assign one we just finished and then this one, both for next Tuesday. But Thursday, after I'm done with that section, then we're gonna talk about the homework questions in class.
Yeah, so these will both be due Tuesday.
These are both due Tuesday, but we're going to talk about them in class on Thursday. See, if it were math, I can explain it much better, but
I get it.
I'm just,
I was just confused at first.
yeah. Oh, well. So, yeah, so again, 6.1 and 6.2, which are definitely chapter 5, section. I'm going to do 5.1 in the book, as I wrote up at the top here. Blah, blah, blah. So this one's 5.1 in the book. We're skipping 5.2. I mean, it looks horrible, so don't even look at 5.2. And then we're going to skip to 5.3. So we'll move on to this next section, which is, this one is 5.3 in the book, not 5.2, 5.3 in the book. If you want to do problems from 5.2, okay, have fun with that. This is 5.2, or 5.3 in the book, section 6.2 though. This homework and the previous section's homework will be due next Tuesday. We'll talk about the problems in class on Thursday. That does not mean I'm letting out class early, or I can use these next 10 minutes to make some progress on this section. So let's go ahead and do that. We'll just go ahead and introduce, well, 2 new formulas. So as you see, there's these 2 new formulas for what's called the sum and difference formulas for cosine. And this allows us to be able to, well, simplify cosine values. We'll see sort of the reasoning why this is helpful, especially as it pertains to exact values instead of approximations. But there's really nothing other to say other than let's just look at these examples and see what the heck this is going on about. Example 1 says use a calculator to verify that these formulas work for these 2 values. I mean, really, I'm just going to use, I'm just going to pick one of these at random. There's no point in plugging both. I didn't say that, never mind. This is one problem. Okay, so what this says is cosine of 43 degrees minus 17 degrees. So if your calculator's in radian modes or radian mode, go ahead and make sure it's in degree mode, because these are degrees. This is cosine of 43 degrees, and we'll do the top formula. This is the difference formula, obviously, because there's a subtraction sign. The very beginning. So let's see, grab my calculator as well. (43 minus 17), we see is 26 degrees. If you put 26 degrees in the calculator, you'll get 0.89, call it just 9. So on one side, we get that cosine of 26 degrees is 0.899. That's what it says on here. So if we apply the formula says that we can write this equivalently. It's cosine of 43 degrees, cosine of 17 degrees, plus sine of 43 degrees, sine of 17 degrees. Notice the sign changes. There's a difference for the cosine of a minus b, and then the formula has a plus sign. Notice there's a switch there. And so now I want to plug all of this in the calculator. And what we're verifying is that this also gives us the 0.899, which I'm assuming it does. So we just verified that the subtraction part works. The addition part is not really too much different. 43 degrees plus 17 degrees. So 43 plus 17, well, look at that, it's 60. That's a special one. It's cosine of 60 degrees. That gives us a half. So this is saying whenever we plug in all the cosine stuff, but we change the plus sign to a minus, we better get a half. Someone already plugged this in? Assuming you did. So example 1 is just a verification problem. Example 2 is more likely the substance to expect in this section. So find the exact value. Again, for those of you who keep giving me approximated values on various tests and homeworks, I'm just going to keep marking it wrong. Exact value means that don't give me an approximated answer. I need an exact value, square roots, things like that. So if you did this problem and you told me that the answer, so don't do what I'm about to do. You told me that the answer was approximate to 0.966. Then I'm going to exit it out and say, you don't get any points. That's cheating. Don't do that. I'm trying to tell everyone right now. On the homework, same thing. Don't do that. Exact value means I need square roots and numbers, whole numbers. So the question is, all right, so how do we find the exact value of this thing when the calculator is giving us this weird decimal approximation? The answer is we need to figure out a way. So what do we know currently? We know cosine of the nice angles of cosine of 0 degrees, cosine of 30 degrees, 45 and 60, and 90 degrees. We know, so these are the special angles to us. So the question is, that 15 there, how can we write 15 as a sum or difference of those special angles? So special angles. 0 degrees, 30 degrees, 45 and 60 and 90. So would any combination of those numbers as in a sum of difference of those numbers, give us 15 degrees.
-30.
Yeah, 45 minus 30. 45 degrees minus 30 degrees. But hey, look at that. Now we have a difference, which means we can use the difference formula. So if you want, you can even say that this one's A, this one's B. And plug it into the formula. I mean, you'll have all these formulas on the test and for your homework. So what the formula says, I'm reading off exactly. Cosine of A, which is 45 degrees. Cosine of B, which is 30 degrees. Plus sine of A, which is 45. And sine of B, which is 30. Now if you think, all right, I'm going to plug that into the calculator, that's still not what you do. Notice now we have broken down this problem into a collection of trig values that pertain to special angles. So if I go through these one at a time, and I mentioned this in the previous chapter, if I type cosine of 45 in the calculator, I get 0.707. I told you that's a decimal you need to recognize from now on, because that corresponds to the square root of 2 divided by 2. That is a decimal you, for now on, you need to recognize. And then the other one was 0.866, which is the square root of 3 over 2. Those are two decimals you need to get used to. If you don't feel like getting used to them, then you will have to derive the special triangle every time. That's why I'm trying to tell you, or you could just memorize them blatantly. It doesn't matter. I don't care. Cosine of 30 degrees. Well, there's the 0.866 that I said. Square root of 3 over 2. And now I see a plus sign, and now sine of 45 degrees. I see 0.707. And then sine of 30 degrees, that's just a half. And by simplifying this, well, the way we multiply fractions, square root of 2 times square root of 3 over 4 plus square root of 2 times square root of, or just 1 over 4, which we combine all this together, square root of 6 plus square root of 2 over 4. And the only reason I write it like that is because the back of the book writes it like this. And you're going to see that form and wonder why your form is not their form. The square root of 2 times the square root of 3, you can multiply the numbers underneath the square root. So it's just 2 times 3 with the square root that follows. We'll talk about this more next time in class. We're going to do a problem pretty similar to this for the next one. And we're going to talk about these in class, so don't think I'm just going to throw you out to the wolves. So no homework for next class period, no homework. So take a breather from this class, no homework, you're all good. Homework will be next Tuesday. And other than that, that's all. That's really all I have today.